Yeah. Okay, thank you. So this is another breakout. I think this will be boring for a few of you, but I noticed that in none of the presentations there was an intro on post-quantum cryptography, but there is interest in it. So I thought I'd put together at least some slides to have some takeaways. And if that whets your appetite, I put some references at the end. Well, we all know that quantum computers are going to break cryptography. The big question is when. And people throw around, there's this new big quantum computer with so many qubits, which is like the size. But one thing you should realize is that quantum computers are analog machines, so it's not just about the number of qubits, but it's about how good they are. They have noise, so there's at least 2 dimensions. And if we're looking at, this is a summary in 2021 of the quantum computers. So on the bottom left, there's a gray area. With on the horizontal is number of qubits, vertical is how good they are, the noise. And if this gray area grows and it hits one of the red lines, we're in trouble. So this is the year after, this is the year after. So the gray area is growing, right? So we don't know. Will it keep growing at the same pace? Will it halt? We don't know. Also, notice that the green area, which came down. So if quantum algorithms get better, then also that can also happen, of course. So we don't know, but governments are worried. So the United States government wants to have the United States transitioned by 2035, which is not going to happen. But I mean, it's an ambition. And the CNSA2, that's the guideline of the NSA. They already require now, if you want to be CNSA2, you have to be PQ. So there's urgency. So another thing that's important is that the urgency is quite different between different types of cryptography. And so for TLS, you have key agreement and signatures. Key agreement is urgent because people can store encrypted stuff now and crack it later with a quantum computer. So you want to upgrade this as soon as possible. But signatures are less urgent, right? We only need to have this sorted once there's a quantum computer. At least in TLS, I mean, you have also long-running signatures in cars or firmware updates, but it depends on your application. Oh, another thing to notice is symmetric key cryptography. Some people say you need to double key lengths. That's absolutely not required. AES-128 and SHA-256 are completely fine. No need to change that. Okay, so key agreement, we are already deploying this. This is the number. This is the traffic, human traffic we see that's already using post-quantum key agreement, and that's now at 18%, and I expect this month it will probably go even higher to maybe a quarter, and before the end of the year I think it might be even 30. Who knows? It will go up. But that's key agreement, so that's nice, but signatures are the pain point here, and also you will feel that signatures are the pain point. And the reason is mostly they are big. So here's a big table, and as you can see, MLDSA, which is the workhorse, that's has a public key of 1.3 kilobytes and a signature of 2.4 kilobytes, which makes it a bit annoying if you want to have a lot of witness signatures in key transparency, for instance. You have Falcon FNDSA, which is smaller, but it uses floating point arithmetic in signing, so also not great. Hash-based signatures are not that great. Either they're also really big and slower to sign. There's also some signatures in an on-ramp, so there's a new competition. So these 4, they're already standardized. There's a few bunch in the new competition. They all, well, the key sign looks nice in the size, but if you look at the CPU time, that's not really ideal. Then another interesting one is UOV, which has nice small signatures, 96 bytes, but public keys of 70 kilobytes. So it's maybe it fits your application, but it's going to be tricky. And this is only signatures and key agreement. If you ask questions about more fancy cryptography like OP-refs, no, you can ask Lena about post-quantum OP-refs, but they're not that great. Of the fancy cryptography, only a fully homomorphic encryption is already post-quantum, but for the rest, it's very, very difficult. Okay, that's what I wanted to give a web chat about. That's it. There's 2 links. Okay. Any questions? Or I think I'm over time.